Hello everyone, welcome to Geology Concepts YouTube channel. I'm here to discuss
with you another important topic, and this time a little bit different topic from the exploration geophysics. I'm going to discuss with you the electrical resistivity method, which is being extensively used nowadays in the exploration of oil and gas and hydrogeology or groundwater, we can say. So the basic idea behind this method is to calculate the resistivity, which is a fundamental physical property of any rock, and this is some physical property which is only going to change in the subsurface when your rock is changing. So of course we will directly relate this resistivity to the type of lithology we are encountering in the subsurface. The basic idea behind this technique is that we provide the current in the subsurface, and as we know that the rocks are somewhat or up to some extent conductors of, not good conductors, but they are conductors of electricity. So when this current will pass through the subsurface and also through different layers of rock, they will experience different type of resistance provided different type of rocks, and hence collectively we will get the potential difference at two potential electrodes that we are placing on the surface, and we will measure the voltage. So by using the current and voltage and also Ohm's law, we can calculate easily the resistivity of the subsurface. Of course, that will be the apparent resistivity because it will be cumulative of all the subsurface rocks. But yes, we will have an FT idea about what kind of rock might be present in the subsurface. So this is how the field is being set up using these 4 electrodes. This is the most basic arrangement of 4 electrodes, but multiple electrodes can be used and can be laid down by using cables for hundreds of kilometers, and an extensive survey of 100 square kilometers can be done using this technique. And also the depth of penetration is quite good because you can get an idea about up to several kilometers by using this technique. So to understand this, we need to have a very basic idea of the Ohm's law, which suggests that V is equal to current multiplied by the resistance. Now, the reason why, because we are not using the resistance and instead of that we are using resistivity, is that resistance is purely dependent on the dimension of the material you are dealing with. But resistivity is something which you can actually relate to the density, which is an intensive variable. This is only going to change when your material is being changed, or we can say the rock is being changed. So the change in resistivity will directly be incorporated into the change of lithology. Now, as I mentioned that we will use the simple Ohm's law to derive an expression of how we can calculate the voltage and indirectly the resistivity at any point on the surface of the earth. So let us assume that if we put an current electrode over here on the surface, so it will generate these wavefronts of spherical or hemispherical, we can say, because on the surface of the earth or above that in the air, current won't flow. So this will produce a hemispherical in the 3D wavefront, which will dissipate like this radially. Now, if I were to calculate the volt, or we can say potential difference at any point, let's say, which is r or dr distance apart, I can write this formula as I, and here also I can write resistivity instead of resistance as shown by this formula. So I can just simplify this for a time bit, and I can write resistivity from here as resistance multiplied by area over the length. So I will write resistance as rho into length divided by area. So as this is a hemisphere, I can write the area for that as 2 pi r square instead of 4 pi r square. If it would have been the complete sphere, it would have been 4 pi r square. Now, if I am interested to calculate the voltage at, let's say, dr distance, so I will write this length as dr here, and also the change in the voltage, because as we are moving away, the voltage is decreasing, so I put a minus over here, and I can write it as I rho dr by 2 pi r square. Now simply, if I were to calculate the voltage over r length, I can integrate both the sides and just simply integrate this dr by 2 pi r square term, right? I can put the value of limits as 0 to v and 0 to r to find the voltage in terms of r, so that I can calculate the voltage at any particular distance from the source. So this will come out to be I into rho divided by 2 pi r, because the integration of r raised to the power minus 2 will be minus 1 by r, and this minus will be accommodated by the minus we already have. So at last we will have a very simple relation of voltage, or we can say potential, with the inverse of the radius we want to calculate this potential to. Now I can use this simple relationship to apply the concept for my 4 electrode configuration in which I'm interested in. So I have taken 2 current electrodes and pointed them as A and B in this figure, where my plus I current is being generated here and minus I over here. And I have 2 potential electrodes, P1 and P2, marked as M and N here. Now, the voltage that is going to be generated at M and N will be a collective voltage, which I can write as Vm minus Vn, the potential difference. And this Vm, this potential at M, will be generated by both C1 current and C2 current. Similarly, the potential will be generated at N by C1 and C2 current. So I can write the formula for Vam, that is the voltage at M due to current electrode at A, simply as I have done, or I have determined in the last slide, as rho into I upon 2 pi r. Now here the r will become the am length because the current source is here and you're measuring the voltage at point M. So this will become the length am. Similarly, Bm you can write as I rho by 2 pi mb. Now I would like to emphasize here that instead of I will write minus I, because the current which is being generated at B is not plus I, rather it's minus I, because this is a circuit where at one electrode it generates plus current, plus I current, and at another it generates its minus or sinking current, that is minus I. So collectively, at if I were to write Vm, I can write as rho I by 2 pi multiplied by 1 by M minus 1 by Vm. So this is the potential which is being generated at point M due to potential, or sorry, current electrodes at A and B. And similarly, I can write this formula or this expression for the voltage which is being generated at point N, such as rho I by 2 pi An minus Nb length, in the same manner which we have used for point M. Now, as I've mentioned, the calculated voltage or potential difference at both the points, or in this complete circuit will be Vm minus Vn. So let's just write that down. It will be nothing but Vm minus Vn, and what we have calculated, I can just write it as it is, rho I by 2 pi, and now I can collectively write it as 1 by Am minus 1 by Bm minus 1 by An plus 1 by Bn. Why this has become plus? Because in the last slide we have seen that it was already a minus, and minus becomes plus over here. So this is what I'm going to get the potential difference using these two electrodes and using these two potential electrodes. At last, what I'm interested in is the resistivity. So for that, I can write down the formula in the terms of resistivity, in which this whole term, which is simply dependent on the geometry of the electrode configuration. Because see, if even for a small change, this AM, M, N, or A or B, any one of these gets changed, then this whole term is going to change. That is why collectively this 2 pi multiplied by this, or the inverse of this, is actually called as the geometric factor, because it is completely dependent on the geometry. Rest all the terms are constant. The voltage, the current, and the resistivity is going to be constant. So this whole factor, we call it as K, or geometric factor, which is only going to be dependent on various geometries you're going to use, or you're going to encounter. Now this was a basic idea which you can use while doing this electrical resistivity survey. Now based on this technique, you can have multiple type of arrays or configurations. Most important or most commonly used arrays in industries are the Venner and Schlumberger array, in which particular the Venner is the one in which the electrode spacing between current electrodes, the potential electrodes, are all same, you can see. So if you put all these values in the formula we have just derived, you can calculate the geometric factor, which is represented here as capital G, which is coming out to be 2 pi A, and you can just simply write it down as del V by I into the geometric factor, which is going to give you the apparent resistivity. In the Schlumberger array, the configuration is such that your potential electrodes and current electrodes are quite distant from each other, or we can say that separation between the potential electrode is quite smaller than that between the current electrodes. So if you are going to deal with such kind of array or configuration, you will going to get a different formula for calculation of apparent resistivity. Similarly, there are others such as dipole, in which you have make two dipoles, or you have taken the potential electrodes all at one side and current electrode at one side. All these variations you can do for the method or for the requirement you have, the depth of investigation you're going to get. So based on your requirement, you can actually vary these, and the most important ones, or the most frequently used ones, are the conventional Venner and Schlumberger array. But based on the requirement of your survey, you can always change this. You can also, apart from these 5, you can actually arrange your electrodes in your own way based on your requirements. Now, this was the calculation part, or the behind story, what actually happens. But what we do after doing all this is the interpretation part. This is quite important part, because you can do the survey, but if you're not good at interpreting the data, then it's a waste. So after doing all these survey, you're going to generate these sensitivity curves, or we call these as ERT curves, electrical resistivity tomography curves, in which you're going to plot the resistivity data in this color chart, which is mentioning the resistivity in ohm meter scale, where the color purple is going to give you a very high resistivity value, and the blue, on the other hand, is giving you the smaller values of resistivity. Based on this, if you dig a borehole and you encounter such type of resistivity variation, the possible interpretation which you're going to make out of this can be so and so. So this will going to give you a very brief idea or very good idea about the lithology that is present, and you can see the depth it had encountered is about 9 meters, which is quite good for the exploration of groundwater, and it is being extensively used because we know wherever you will find water, you will going to get the low resistivity. So hence you have these color chart with you, and you can also use different type of charts to mention the different resistivity values. Also, you can see that the resistivity variation is quite large. I mean, from very low value of 0.001 ohm meter to about hundreds of thousands ohm meter, you can have the resistivity based on the configuration of your or mineralogy of your rock. So resistivity is one physical parameter which is having a wide range of variation. So once you get the resistivity values or the variation in the subsurface, you can very well correlate this chart with your variation, and you can have a very good idea about the subsurface lithology. So this is a very brief or summary of how does this type of method is being used in the exploration techniques. So I hope you liked the video, and also, in the last, I would like to mention that we have started our Gate and Net online classes, which are being conducted daily, Monday to Friday. And for that, you can also join the demo classes that are free of cost. Register for those demo classes, fill the form in the description given down below. And also, if you like the video, please share it with your friends, subscribe to our channel, and stay tuned to Geology Concepts. Thank you so much.